we proceed with just a little bit of notation and a little bit of an introduction to the calculus of matrix functions. The calculus is actually pretty easy. It's not something that I find that students really have much trouble with. Okay, the vector function. Okay, let A of t, I'm sorry, matrix function. A matrix function of t consists of a matrix whose entries are all functions of t. Now the typical notation for a matrix is to note its, let's bring this down here a little bit because I have kind of an inconvenient angle when it's up there, and centers it for you also. Okay, a matrix A can be written as n rows, each row consisting of n entries. Okay, and of course this is an n by n matrix, that's implicit. We list the entries of each row by keeping the number of the row the same and changing the number of the column, so that the first row, first column is A11, first row, second column is A12, and the first row, nth column is A1n. And our typical element is Aij, where I stands for the row and j for the column. Our last row will be the nth row, so we have nth row first column, nth row second column, nth row n column. We abbreviate this whole notation by just putting brackets around A sub ij and specifying, and usually it's implicit within the context, that I runs from 1 to n and j runs from 1 to n. Now this, again, also assumes a square matrix. We don't have too much dealing with non-square matrices except for row and column matrices, as we'll see. So most of our larger matrices will be square matrices, but of course if the matrix isn't square, then we could use m for the number of rows and for the number of columns, and then I would run from 1 to m and j from 1 to n. In any case, matrix function of t is one for which all these aij's are also functions of t. So each of these could be polynomial, a trigonometric function, an exponential function, any of the standard functions, even completely weird functions, although most of what we'll deal with here are pretty standard functions because they're the ones that arise in the kinds of equations we can actually solve. So with that introduction to the vector function, to the meaning of a vector function, we can define the derivative of a vector function. The derivative of any function is the limit as h goes to 0. Well, the derivative of a vector function for t at variable t is the limit as h goes to 0 of that function evaluated at t plus h minus the function evaluated at t, that being the difference of the function, the change in the value of the function between variable t and variable t plus h, divided by the value of h. So that this gives a rate of change of the function with respect to t. Now, for a vector function, we simply take this operation inside and apply it in turn to every one of the functions, so that aij represents the typical function that makes up this matrix, but this applies to any I or any j, so that what this tells us is we simply take this same limit for every one of the functions in the matrix. And I'm not going to read that to you, but that limit for any one of the functions is just the derivative of that function. Now there are questions of domain. The derivative of this function can only be defined on a domain in which all of the functions here have derivatives. If there's any function that doesn't have a derivative at some value of t, then that value of t is not going to be in the domain of the function of which we take the derivative. Another way of saying that is we only take the derivative of those functions we can take derivatives of. for values of t for which that's possible. Now, I assume you know how to add matrices. If you don't, review it. But if we do a matrix A plus B and take the derivative of that matrix, without any further comment, I'm just going to say that that's equal to the derivative of the first matrix plus the derivative of the second matrix. In other words, the derivative of the A plus B matrix is the matrix you get if you add the derivative of the A matrix to the derivative of the B matrix. And I could also state the whole linearity condition, which is just that the derivative of some scalar multiple of A and another scalar multiple of B is just that scalar times the derivative of A plus the other scalar times the derivative of B. Not written very well. And these are common operations that, given two matrices and scalar multiples, you would probably apply without even knowing that you have to have permission to do so. Okay, these are just things that you're naturally going to do when you start dealing with matrices. Again, this is not something, these properties are not things that ordinarily give students who have a literate calculus background any problem. Now, one that can cause a little bit of pause is, what if we have some function multiplied by a matrix? What does it mean to multiply something by a matrix? Well, to multiply a function by a matrix, we multiply that function by every entry of the matrix, by the every one of the functions that makes up the matrix. So that, first in place, f of t times a of t is the matrix that consists of ij components, f of t, aij of t. And the derivative of f of t, aij of t is just obtained by the product rule. This is just a product function. For every ij, this is a product of f of t with some function aij of t. So we just apply the product rule and we get f prime aij plus f times aij prime. Now the matrix whose ij entry is this is the sum of the matrices with ij entry f prime aij and f aij prime, and the f can then be factored out for the same reason it could be multiplied in, and what we then end up with is f prime times the aij matrix, which is just the A matrix, and f times the aij prime matrix, which is the A prime matrix, so that the derivative of f of t, a of t, is just f prime times a of t plus f times a prime of t. The formula looks exactly the same as it would for two functions of a single variable. So we do have a product rule for multiplication of a function by a matrix function. It shouldn't be any surprise. I'm not going to write out the details. I didn't write out all the details of this. I just kind of alluded to them. But if we have a matrix function A and a matrix function B, the derivative of that product function is the derivative of the A matrix multiplied by B plus A multiplied by the derivative of the B matrix. And the integral of a matrix is just the matrix we get when we integrate all of its components. Once more, for probably at least the third time, these operations become very natural if you're conversant with the calculus of plain old functions of a single variable. All the properties are just what you would expect them to be. To prove these properties takes a little bit of notation. To prove this one, you're going to have to do some notational tricks. It gets a little complicated. If you've had linear algebra, there'd be nothing daunting about proving either this or this. But when you look at the examples in the book and do the problems, I don't think any of this is going to give you any real trouble.